So good morning, my name is Will Chueh. I'm a faculty member in the Material Science and Engineering Department here at Stanford. I'm also a member of the Preocurt Institute for Energy. And it is a great pleasure and honor to moderate this next session on energy storage and conversion. It's really a great pleasure to introduce some of my colleagues in this area and learn about their research. So I was asked by GCEP to give a quick overview. This is really a difficult task because energy storage conversion is such a vast topic. So it really presents it's a really difficult one to think about how to organize and tie the talks together. So I'll give it my best shot here. So I like to say that electrochemistry and electrochemical process is at the heart of carbon neutral energy cycle. But my colleague and friend Mike McGee told me it's really not a good idea to think about electrochemistry as the heart, because it's not just doing the job of circulating, say, your energy carrier. He encouraged me to think of electrochemistry as fat or producing fat. So I think that's a really interesting way to think about the biological analog of electrochemistry. Needless to say, what is really important is that electrochemistry plays a role almost in all aspects of energy storage conversion. So what I have here, it is a quick slide overviewing some of the technology being pursued here at GCEP, looking at a carbon neutral cycle that starts with the sun. You can also start with other forms of energy. This is just one example. What I want to highlight here is there are 4 elements to a carbon neutral energy cycle, starting with capture, storage, delivery, and utilization. And what we will hear about today from 3 speakers are electrochemistry and electrochemically active materials for energy storage in the form of batteries, for the conversion of water to hydrogen and oxygen. So we can also view that as a storage process as you have a dispatchable fuel, such as hydrogen. Then after all this fuel is made, you have to have some way to convert it back to electricity, and that is the fuel cell aspect of the energy conversion cycle. So you'll learn about how critical materials are for enabling high efficiency, low cost energy storage conversion in these 3 areas. So I thought it was fun to think about where things are at today. And I made these 2 plots, one for energy storage and the other one for electrocatalysis. The left plot basically shows you the inevitable trend that we're trying to battle. If you look at energy storage such as batteries, on the y-axis you have reversibility, so this is the number of times you can recharge your battery. And on x-axis you have energy density. It's almost always as you increase the energy density, the reversibility falls. This is the battle that we're trying to fight. What you will hear from Zenan and Hongjie are new material approaches to reverse the trend. So how do we increase the energy density and at the same time increase the reversibility or the rechargeability of the system? And this really underpins one of the greatest challenges with energy storage. In energy conversion, for example, in electrocatalysis for dissociating water into hydrogen and oxygen with electricity, you're also faced with a very similar challenge. The x-axis is the activity, so how good the catalyst is, and the y-axis is stability. So inevitably, as you increase the stability of the material, as you increase the activity of the material, you decrease the stability. And what you'll hear from Hongjie and Reggie is developing material that goes the other way. So can we increase the activity, but while maintaining excellent stability? So you'll see that in the y-axis, this really concerns with the efficiency, scalability, and cost of energy conversion and storage. So we can do a lot in the x-axis, but y-axis is the key challenge here. We have Professor Hongjie Dai from the Department of Chemistry here at Stanford. And Professor Dai is very well known for his pioneering work in carbon nanotubes, but in recent years, he has been expanding into the areas of nanomaterials for energy storage conversion. And over the past few years, has developed a new material for battery, new material for electrocatalysis, new material for water splitting, some of them under the support of GCEP. And today, he's going to take us through a journey looking at some of these materials and how nanostructuring it can really lead to interesting new property in terms of the efficiency, stability, and reversibility of these materials. Hongjie, please.
Okay, good morning. I'd like to thank Will for the great introduction and GCEP for the invitation. My group really came from materials chemistry and physics angle. to study energy problems. So I'd like to tell you the work that's going on, after we spend a lot of time working on carbon nanotubes and see how novel carbon nanomaterials can be useful to expanding from carbon to new kinds of materials and for electrocatalysis and battery. So I'm sure this really doesn't need a lot of introduction, but I think everyone working in this field is really to look at ways to harvest energy from nature, using them in a very meaningful way to improve our society. So you really would like to have materials or devices that can harvest the solar energy, so you can have very good solar cells, so you can have electricity from the sun. But quite often, your energy can, you cannot use all this energy or all this electricity, so you would like to store them. In that sense, you would like to have very good batteries, okay? Or you could think of ways of converting solar energy or wind, hydro, that we have a lot of in nature, into chemical energy, right? Like make very clean hydrogen fuels. So everything here really comes down to materials, catalysis, okay, electrodes. How do you make things better, more stable, at lower cost? So the two main areas in my group to approach these materials problems in renewable energy is really in two areas. One is make electrocatalysts that may be more active, more stable, as Will was saying, but also at a very low cost, okay? And so that's one of the areas. But then we also would like to make batteries that may be a little different from what we had before, right? So people have been improving lithium-ion batteries over 30 years or so and making progress steadily but very slowly. So can we actually have new kinds of batteries that runs with different materials, maybe at much lower cost, maybe we'll have less safety issues than lithium-ion batteries. So I'd like to share with you the story we had recently on making aluminum-ion battery, okay? All right, so the first topic is really about splitting water into hydrogen and oxygen, and I think it's really something that most of us, if not all of us, have done when we were kids, right? So we take water, put salt in it, and put electrodes into it, and try to apply a voltage and get hydrogen and oxygen gas out of these two electrodes. Now, there are two reactions in this system. One is hydrogen evolution, which is HER, okay, hydrogen evolution reaction, and the other one is oxygen evolution reaction. So both have to happen at the same time, and theoretically, the voltage you would need is only 1.23 volts. Okay, so it's relatively low energy to get this reaction to go, but in reality, you actually have a lot of so-called overpotential. So you really have to supply more voltage than necessary thermodynamically in order to get these gases to evolve. And simply because these are really multiple proton or electron processes, so there are lots of kinetic barrier you have to overcome, okay? So for these reactions, typically you would need precious metal as the catalyst to get very high activity, okay, to lower the overpotential. So for the hydrogen side is typically platinum being the best catalyst, and then for the oxygen side is the iridium oxide as the best catalyst, okay? So in that case, you would be able to get a 1.5 to 1.6 volt to get these two reactions to happen simultaneously. And in industry these days, for this water splitting in basic solutions, in order to lower the cost, typically the catalyst for HER is nickel. Okay, nickel is very abundant and low cost. And then the electrode for oxygen is stainless steel, which is also quite abundant and quite low cost. But the caveat is that activity is quite limited. So you would need high voltage, like 1.8 or even 2.2, 2.3 volt, in order to have large amounts of hydrogen and oxygen. So we would like to have cheap and scalable catalysts, okay, so that you can get water to split at very high energy efficiency. It doesn't make a lot of sense if you really had to use a lot of electricity to make hydrogen, okay, with a low efficiency. So my group over the past 3 years have identified a few materials that are pretty active for water splitting reactions. So this compound here is called a layered double hydroxide. Okay, this, by the way, has a series of compounds. There are many LDHs out of different kinds of transition metals you can make. Okay, people have been studying LDH for decades for a lot of scientific or engineering applications. But rarely people tried using this class of material for electrocatalysis. So a few years ago, we stumbled onto this material. So this really is like, if you're familiar with the graphene, it's very similar to that, but it's an inorganic version of it. So you have these sheets of hydroxides that's stacked together, and you can make very thin plates of them. And you see these octahedrons really just have nickel in the middle, or some of them would have iron 3+ in the middle as dopants, okay? So this, by the way, was grown, these plates were grown on carbon nanotubes because we would like to have a network of carbon so that the material is very conducting, so it gives us even better activity. So they would look like this. Okay, the nanotubes are swiggly, and you have these very thin plates sitting on the tubes. And now if you look at the activity to produce oxygen, it's actually quite good. So the red curve here is the current associated with oxygen production. And you can see the voltage needed is actually lower than uridium. Okay, uridium is the gold standard for OER. Okay, it's more active than uridium in basic solutions. This in KOH solution. And what's more important is it's also quite stable. So this is a constant current curve. You can see with the LDH, it's actually the voltage you need to produce oxygen is stable. Okay, it doesn't decay. But for iridium, it actually decays. So there's a stability problem for iridium. So this is really quite active. It's not quite 1.23 volt. Okay, you still have 200 millivolt, 250 millivolt over potential because it's a 4-electron process. So there's a lot of kinetic barrier. So this, after it's published 2 years ago, it's actually very quickly reproduced by many groups in the world, including prominent groups like Michael Gretzel, and they made LDH exactly like ours, and found that this material is good for oxygen evolution, but also it's quite active for hydrogen evolution. So you can actually use it on both sides to get hydrogen and oxygen out. And then also they were clever to put a very new solar cell, perovskite solar cell, to harvest the solar light and drive the hydrogen and oxygen production using the LDH electrodes, okay? Getting a very good efficiency of 12.3%. So what that means is that you take sunlight, 12.3% of it goes into producing hydrogen and oxygen, which is a fairly reasonable efficiency. okay? All right, now let's talk about the hydrogen side, okay? LDH is pretty good, but it can be better, okay? So we looked at this, this side, and many people have looked at it over the years, and the best is platinum in basic solutions or acidic solutions. And the hydrogen electrode is actually very important in the industry. I don't know if you're aware of it. Other than using it for electrolysis, which is to split water, people actually have been using it for decades to make chlorine gas, sodium hydroxide, okay? These are very important chemicals. So that's the so-called chloroalkali industry. So there's industry around us for that. So one side you produce chlorine, the other side you need to produce hydrogen. And this is extremely energy consuming process. Okay, it actually consumes about 8% of the electricity in the United States, 8%, just for this single reaction. So you do have a need actually to lower the energy cost or the overpotential for hydrogen evolution. And so far, in industry, nickel is the metal that's used for HER, okay, in basic solutions. So recently we found that you can actually do better than nickel, okay, if you make a material that contains nickel and nickel oxide, okay. So we identified a material that looks like this. It's basically look like nanoparticles, but it actually has nickel oxide. So the green part is oxidized nickel. Okay, it's like a shell on the outside. But then the middle, the red phase is actually metallic nickel. Okay, so you make these, what we call heterostructure. You have nickel oxide attached to nickel metal, okay? So this material turns out to be very, very active for hydrogen evolution reaction. And we have done theoretical calculations on that with collaborators. And what's happening, we believe, is actually when you do have hydrogen evolution, the hydrogen atom can actually attach to the metallic nickel side, okay? And then the OH groups, which are oxidizing species, they actually attach to the nickel oxide phase. So that boundary of nickel oxide is what we believe is the really active site for producing hydrogen. And now with these two electrodes, one for hydrogen and one for oxygen, you can do this experiment again as you did in high school, okay, and use two electrodes to produce gas bubbles. I'm not sure if the movie is playing. Oops. Take a look here. Is it playing? Okay. Maybe there's some technical problems with the... Yeah. So you can see gas bubbles, right? Yes. So this now is only driven by a single alkaline battery. Okay, so it's 1.5 volts, which is not easy to do if you do it at home, okay? Typically, you would need at least 2 alkaline batteries to get to about 3 volts. Then you will see a lot of gas bubbles. And this is good because you're using very low-cost catalyst, right? So you're using nickel oxide, and iron. Okay, it's a very active and very stable electrode material. And more recently, we went a step ahead and coupled it with a very good solar cell, a gallium arsenide solar cell, okay? And we're able to achieve about 15% of efficiency. Okay, so 15% of the sunlight is now going into producing hydrogen and oxygen. And what I want to point out is really look at this red curve here is the 2 electrodes we made. And you can see we only need about 1.7 volt or so to produce 200 milliamp per centimeter square current. okay? So that's a current that you really need in industry to make these gases, okay, 1.7 volt. If you don't use these catalysts and use conventional ones, nickel and stainless steel, and that's what you need. Okay, you need about 2.4 volt. So that's a very large reduction in the voltage you need to produce the gases. So what's also important is that it's quite stable. Okay, you can do this for 500 hours without much decay. Okay, so we figured out ways to stabilize these catalysts. And we also are able to drive the water splitting using lamplight. Okay, you can do this at night. You don't need solar light. So here's a video you can, if we place, try this again. Yeah, so that's the solar cell. We're using a lamplight to shine light onto it, and then you can see the two electrodes here are doing their job. Okay, so you can make quite a bit of hydrogen and oxygen using lamplight. So what that means is that at night, if you have a lot of wasted light or straight light, you can somehow collect and feed them to these electrolyzers and make hydrogen and oxygen. Okay? All right. So we also have other types of catalysts for electrocatalysts for oxygen reduction reaction, which is useful for fuel cells. I don't want to go to a lot of details of this, but here's one, cobalt oxide on nanotube. It actually can be more active than platinum in basic solutions. Okay, so again, these are very simple materials, cheap materials that you can utilize to make a very active and stable catalyst. So let me switch gear to batteries very quickly here. One battery I want to mention is zinc air battery, which is the one that actually is supported by GCEP. The reason we're working on zinc air battery is because it has very high energy density. Because if you oxidize zinc, you can get a lot of energy out, okay? But the challenge is, can you make it rechargeable and can you make it energy efficient? So there are a lot of issues with zinc air battery, but what we worked on was the electrocatalysis side, because we have good electrocatalyst, okay? So we use our electrocatalyst to increase the energy efficiency of a rechargeable zinc air battery. So this is our catalyst cobalt oxide on carbon nanotubes. This is our LDH nanotube for oxygen evolution. So you combine them and you use them for the zinc air battery, you get pretty good performance. Okay, so this is a rechargeable zinc air battery over many cycles, and potentially this can really lead to very high efficiency, well, higher efficiency zinc air rechargeable battery in the future using these electrocatalysts. And lastly, I want to tell you this aluminum ion battery story. So this was a project we started about 2 years ago, and we had very low expectation at the time, but now it looks like we can actually make a pretty good battery using very abundant and low-cost materials, okay? So now you can actually take aluminum foil that you can buy from Safeway, okay? And graphite powder you can buy from Alibaba or anywhere, from your pencil lead, whatever. And then these two are the two electrodes, but this electrolyte is actually a little special. It's made of salt. Okay, there is organic salt plus aluminum chloride. Remarkably, you mix them together, it makes a liquid. Okay, because there's so much entropic gain by mixing intimately, it actually lowers the melting point a lot. So it becomes a liquid at room temperature by mixing solids. Okay, it's fairly remarkable. But we didn't do this part. This is known for 30 years or 40 years. Okay, ionic liquids. And if you mix them in the right ratio, it's also known for many decades that you have these ions. You have aluminum chloride ions. So with this recipe, it looks very simple, right? You can actually put them together and make a battery that works pretty reasonably well. So this side is essentially aluminum foil being oxidized, right? So this side going this way is oxidation of aluminum, or it can be reduced. Okay, you can reduce and make aluminum. And in fact, this reaction has been studied for decades for electroplating of aluminum metal. Okay, it's an electrodeposition technique in ionic liquids. And people have known this, and they have also looked for an electrode that can couple with aluminum to make a battery. That has also been going on for 30 years, 20 years. Okay, so what is the best electrode you can use to combine with this reaction to make a battery? So that's been a very old problem. And 2 years ago, we actually tried about 150 compounds on this side. Okay, try to combine with aluminum. But at the end, we accidentally found that if you mix graphite into some oxides and try to make a battery, you actually get some battery behavior, and you get some capacity, okay? And then we figured out it's not the oxide that's giving the capacity, it's the graphite. So it's a very accidental result. Okay, we add graphite because we want to have conductivity on this other electrode. So now we know what's going on. It's actually these anions, okay, that's actually intercalating in between the graphite. And when this anion goes in, this side has to be neutral, so the carbon gets positively charged or gets oxidized. Okay? And when the anions come out, they get reduced. So it's a very classical redox reaction in electrochemistry, oxidation and reduction, and it's reversible. The intercalation here it's reversible. Actually, it's reversible for thousands and even 10,000s of cycles. Okay, we have data now on that. And the voltage between these two redox couples is about 2 volts. Okay, it's not great. It's not as high as lithium-ion batteries, but it's 2 volts. Okay, it's enough to drive the water splitting we have in the lab. It's higher than alkaline battery. So that's the simple version of this battery, and you can see these charging and discharging curves to look at the intercalation process. The Coulombic efficiency is pretty good. We can get now to 99% okay? And cycle life is good. This is 200 cycles, but we have much higher cycle life data now. And the cathode capacity was low, was about 60-some milliamp hour per gram, and now it's up to about 100 milliamp hour per gram. Okay, by engineering the right graphite material, we're able to increase the energy density of this battery. And what's also interesting is that if you make the graphite side porous, okay, like in this case, we have these porous graphitic whiskers in the electrode, you can charge and discharge very quickly. Okay, so this is a very high current charging, and we can charge and discharge less than a minute, okay, to get this battery to go. And the paper, the cycle life here is about 7,000 cycles, but now we have much longer data. Okay, and then we also have done X-ray diffraction studies to look at the anions going into the graphite for intercalation You can see the D-spacing gets expanded or compressed, and it's more or less reversible from the XRD. If you charge the graphite and burn it up, right, oxidize the carbon, you end up with aluminum oxide. It turns into aluminum oxide foam. You can do XPS to look at the oxidation of the carbon. So this is a pristine graphite. When it's charged, the N is in. Graphite is oxidized. You see that shoulder, that's the oxidation peak of carbon. And when you discharge it, it reverses. Okay, so a fairly reversible redox reaction. All right, so this is the battery, and I think some of the features I'd like to point out is the following. It really uses the most abundant things on Earth, right? Aluminum, carbon, we really have them in everyday life. So this is very friendly and very cheap, and aluminum is also safe. It doesn't combust as easily as lithium. And the ionic liquid is a little special. It's the most expensive part of the battery right now. But even with this ionic liquid, we can lower the price to about $20 per kilogram. Okay, the companies that quoting us this price. But we also have new data now in the lab. We can actually use new ionic liquids we haven't published. That's really dirt cheap. Okay, you can use something that's maybe a few bucks a kilogram to make this battery. Okay, so everything becomes very, very low cost. But it actually still have all those interesting features, including safety. It doesn't really burn as you drill through. We have videos for that. And it charges fast. You can charge in a minute, and you can discharge in 10 minutes or half an hour if you want. Okay, it cycles very well, up to 10,000 cycles. And this is the theoretical energy density, okay, 62 watt-hour per kilogram, including all these active species. So energy density-wise, it's not great. Okay, it's not supposed to be a competitor of lithium-ion batteries. But I think it's actually a pretty reasonable one to think about replacing lead-acid batteries, which actually holds the largest market of battery. Okay, it's more market share than lithium-ion battery. So we hope that this can be useful in the future for grid storage. You could also think of having them at home, okay, because they're safe. They wouldn't catch fire as easily. And you could think about heavy mechanical tools using such a battery. All right, so that's my talk, and we are now actually having all those materials, and I think it's actually quite meaningful now to talk to potential partners in the industry, maybe some in the audience here. But we're already talking to some renewable energy companies who, for instance, have maybe windmills on the ocean because they have electricity, and then there's a lot of water around them. Okay, you can think of making hydrogen using the windmills, right? So we're talking to some of them. So you can make hydrogen with very high efficiency and using water that's very abundant, not necessarily fresh water, right? Fresh water we don't really have in California, right? But we have ocean around us. And we also hope to have batteries like this to become really useful. And I think working with people in the industry would make that happen. Okay, so I'd like to thank the people in my group who did the work, as well as the collaborators here, as well as in other countries. Thank you very much.
Thank you, Hongjie. I think we have time for one quick question.
How would you compare this to flow batteries and lithium-ion batteries in the energy storage space? Because those would be, you could replace those and some of the considerably cheaper. We need an awful lot of grid storage, so that would be wonderful if you could do that.
Yeah, I really think the low cost would be one of the major features of this battery. I don't really have all the cost analysis. It's such a new battery we're dealing with. But all we are trying to do is really to see what are the alternative or optimized components would be in this battery. And we're very excited, actually, as of yesterday, we had something that's much better and looks like much cheaper for the electrolyte. So.
Okay, Hongjie, thank you again very much.